Ladies, gentlemen, lecturers, professors, shush. Okay, this is going to be a somewhat different talk than the last one I gave, the last two I gave. Ellen Zweibel gave a talk on shock acceleration, which I'm having trouble with this, which was exciting because I wrote my undergraduate thesis on shock acceleration, handwritten if anybody wants to read it, including pitch angle scattering and all those things that were new when I was a student. She also referred to going to see some Rounders game, I think it was, yesterday. I'm glad to say that a significant number of you actually went to the climbing gym. That was good, instead. And I apologize for being so pathetic if anybody was watching me falling off the overhangs. But I've given 10.5 talks in the last 2 weeks. Okay, so this is the outline of the talk. This is about software. It's also about project management and various other things. Astronomy is going in the direction of larger and larger projects. Theorists may believe that they're going to be able to continue to do little projects by themselves. I doubt if it's actually true. You're going to be running Athena. You're going to be modifying Gadget or something like that. So this started out with a conversation I had with Michael Perriman, who was then the PI of Gaia. Gaia is an astrometric satellite that's now in orbit, out at L2, about Hipparchus. Hipparchus was his previous project. It was very nearly a failure because they forgot to remove a grounding strap off a rocket. At least that's the story I've heard. And it ended up in the wrong orbit. So he said, I'll buy you a beer, and if you tell me the 10 lessons you learned from the SDSS, I'll tell you what I learned from Hipparchus. And our lists were really quite similar, so I converted that into a talk. So, lessons I learned from the Sloan. But first, what was important about the Sloan? The answer is it was the ugliest telescope in the world. It really is a very ugly telescope. Lots of nitrogen electronics. That's Jim Gunn. Really, a very pretty camera. I mean, look at those CCD filters. It's now in the Smithsonian, so we're not actually using it any longer. A small team who built the project. That's me. I've lost my coffee mug. If anybody sees my coffee mug, that's my coffee mug. This is Jim Gunn, who is the lord of the project. And a larger team of astronomers. And lots of papers. This is out of date, but many papers. And of course, the interesting thing about Sloan was there were large samples. So this is what the data looked like before Sloan. People plotted diagrams, they drew lines on them, and they said, there are clearly populations here which are different from populations here, and you squinted at it. If you make the same plot post-Sloan, it's reasonably easy to believe that there really is one population and another population. That's 150,000 objects. And of course, the large samples also let us detect things like the BAOs. This is the CMAS. This isn't the original detection. We can measure W triple prime, the number of digits in zeros in -1, all that sort of thing. And of course, we were also finding rare objects. So if anybody can see the quasar at 6.4, you've got better eyes than me. And the answer is here. Oh dear, we're going to have to turn that off. Let me see, how do you do this? I think that'll do it. Okay, so there's a redshift 6.4 quasar, and it's that spot there. So, another acronym. SDSS is one acronym, LSST is another. We've gone on to 4-letter acronyms in this advanced state of the field. The Large Synoptic Survey Telescope, a very stupid name indeed. If you want to know what synoptic really means, it comes from the Greek, but astronomers think it means a time-lapse view. Okay. I guess we didn't take enough Greek in high school. So the project is split into 3 sub-projects. This will become interesting in a moment. The telescope, the camera, and the software. There's a picture of the telescope. There's a picture of the CCDs, these 2 out of 189 CCDs. This is actually the mounting plate for it. We're actually building hardware. The data rate should worry you, 3.2 gigapixels every 17 seconds. That's 400 megabytes a second. And software. Okay, so those are the projects I've been working on. In the context of those 2 projects, what did I actually learn? So I wrote these down in 2002, when most of you weren't born or you were in kindergarten or something. I can't help it. That's because you're... Anyway, we'll come back to that in a moment. Some of these are totally obvious. You're going to sit there thinking, but I knew that. That was stupid. But that doesn't mean that really quite smart people didn't ignore these lessons. So they're worth paying attention to. At least I think they are. First of all, project management. As you work in larger and larger projects, you're going to need somebody who actually tells you what to do. You need a boss. You may think that's your thesis advisor. Your thesis advisor probably isn't a very good project manager. We never manage to take technical decisions unimpeded by politics. That's not a good sign. Somebody says, I am going to write the neutrino transport module from your code. And you say, they're incompetent. They can't do that. And they say, and I've got $2 million from the NSF to do it. Then you say, yes, you can do it. I'm joking. But I'm not. That's the way these big projects are indeed run. If you look at something like Gaia, well, Gaia wasn't so bad. Euclid is a satellite going up to do the near-infrared work from Europe. The work on the project is being split up according to how much money different space agencies have put into ESA. That is probably not the way you would optimize the scientific output from a satellite. Okay. Good advice for students. Don't go into projects that aren't fully funded. If your advisor says, I've got 6 months, why don't you start working on this project? It'll take you 5 years to finish it. 6 months money, that's probably not a good idea. Problems to do with somebody doing neutrino transport because they got a grant are worse when you need to be nice to them because you don't have the money to do it yourself. So, first of all, I flouted this rule when I started working on LSST. I started working on the project before it was funded. It now is funded to the tune of more than you want to think. If you don't have enough money, you really need to have a better manager. Okay, so I also no longer believe that all you need is managers. They come from a different world. They're very strange people. Very strange indeed. In fact, you have to learn how to manage them. You have to learn how to manage the boss in these big projects. Scientists aren't good at that. Scientists are good at thinking about other things, typically. And there's another thing there. So now we come to Roberts' paradox. Okay. Unfortunately, it's not named from me. It's named for Eric Roberts at Stanford. I'd like it to be named for me. This is a URL if I put my slides up. So the paradox is there are unemployed software engineers, and there's a shortage of software engineers. Okay? And the resolution, of course, is that the best software engineers are very much better than the less good software engineers. This is a quote from Eric Roberts' report. The best software developer can do the work of 10, 20, or even 100 run-of-the-mill employees. I'm not sure you're allowed to say run-of-the-mill employees any longer. A single-person company that attracts such a superstar, blah, 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 blah. I used to say that the dynamic range in Sloan was minus 100 between the people who made small negative contributions and the people who made very large positive contributions. It's not true, of course, because the occasional really well-balanced person can make 0 contribution. Then you divide by that and you have an infinity. So I don't quite know how to rephrase that. But it's certainly true that people who are good at this stuff are very, very much better than people who are not good at this stuff. Okay, how do you manage projects? This is perhaps not so relevant in this audience, but if you're doing hardware, you design everything, including every detail. What size of screw you're going to use? You're going to use imperial threads, you're going to use metric threads. We made that mistake on Sloan. Anyway, once you've finished designing it, you're done. You build it. In software, of course, you design everything, including every detail. Am I going to use unsigned ints here? Am I going to use shared pointers or unique pointers there? Then you're done. You've finished taking all those decisions, you've written all the code, and it's done. So all the work goes into the design, and none of it goes into the building. That's not literally true. So the real difference here is that building a system is slow and hard, whereas in the case of hardware, because you have to pour concrete and wait for it to set, and you have to blow things up and all that sort of thing. We don't get to blow things up. It's very sad. I didn't put the movie in about blowing the top of a mountain for LSST. Whereas if you're a software guy, designing a system is what's slow and hard. That's what your thesis is about, typically. So how should we manage a project like this? Basically, requirements and reviews work well because if you're building hardware, it doesn't push the state of the art. Whereas software is different. Why do you need to know about this if you're basically a theoretical physicist? It's because people will tell you, why don't you just go out and hire people? Why don't you go out and hire a programmer to rewrite your code? You can just do that, right? Write down the requirements and go out and buy people. And you can't, because you don't know what you want to do until you're basically at the end of it. So this is a real problem when you're getting into larger systems, that there are people typically out there who don't understand what it takes to write code. And I will point out that if you ignore my paradox, or at least Eric's paradox, they never will be written. So another way of saying that is that software holds its contingency in people. Contingency is your spare resources you have when you run out of time. Or you say, I need more money. I need more concrete. Well, that's okay. You can hold that in dollars. If you suddenly say, I need more people, it takes a year or two to find them and a year or two to train them. You have to hire people early. Okay. Next, don't generate an inverted management structure. So that means that the people at the top don't think they're better than the people at the bottom. This is not quite so obvious. On the Sloan, somebody came into my office at one point, in fact, the director of the project, and said, Robert, is what you do difficult, or is it like 5-finger exercises on the piano? And I said, well, I had to think about this a little bit. But that meant the director of the project had no clue that what we were doing was difficult. They thought, as I say, you just go out and hire someone to do it. And that is a problem. It's a problem if you've got somebody who thinks, I can hire a programmer, I can tell them I want to do MHD, and they'll produce an MHD code. You need somebody who's actually done it to get into the trenches. Okay, so this is still a problem. I worry that there are people, senior management still has to pay attention to people, even if you have a title like, whatever my title is, pipeline scientist, I think. In fact, anybody who ever says senior management to you, you ought to be very careful about. They probably wear a suit as well. You have to be careful with people wearing suits. Anybody here got a suit on? No, I guess not. So, software efforts are too largely run as monoliths. So you end up with dividing and conquering. And in fact, after you've divided and conquered, you probably have a far-flung empire scattered across the world, across 10 or 15 time zones. That's problematic. We're not very good at this. We're not very good at saying, I need this, but you're busy. How do I make you actually deliver that? Tools, help, travel is still essential. You're going to need a travel budget when you do your big project. So, the next thing everybody says is, I'm going to review things. And you have to actually fail reviews. People never fail reviews. It's essentially, as far as I can tell, impossible to go into a review and say, this is junk. That doesn't work. You can't do that. Because somebody's going to be embarrassed, and somebody's a friend of somebody else, and it'll look bad. And if you get a report that says, this isn't working, then you'll lose your funding. So you have to say, this is doing remarkably well, and it needs a little bit more effort around the edges, is typically what these things say. You need to put resources where they're needed, not where it's politically convenient. Saying that something's broken is not a conservative approach, although it sort of pushes things over the horizon. It's the horizon effect that used to make chess programs weak. They would avoid checkmating by going round little circles, and then 3 moves later they discovered you were checkmated anyway. And a corollary of, well, hold reviews if you want to learn from them. So what's the view from 2016? Nothing. Nothing has changed. Since kindergarten, nothing has changed. They're about institutional loyalties. They're about people. Money and people are a bad combination. So let's do some software engineering. This is the lesson from 2002. Standard software practice is necessary. What am I going to say? Source code at the level of files, CVS. See, Peter. Peter's from 2002. Code control at the level of releases that can be reconstructed. You don't want to say to somebody, oh yeah, that version, what version are you running of Athena? Oh, I think that had a bug in it. That didn't conserve momentum. Oh, you sure it's that version? Which version did I give you? you can control that by using your tools to make sure you know exactly what you did. Some people say you need to go in at the level of saying which version of which compiler you used, which version of glibc you used. I think that's paranoia myself, but it's not totally crazy, because people do change back-end libraries and they put bugs in. You need rules about tests. I gave a talk about testing on Wednesday at Peyton Hall, which 2 or 3 of you attended. You need to track bugs. We use NATS and NATS Web. You need to adhere to standards. I hear too often people saying, I don't need to worry about whether that code's correct or not. It compiles on my platform. It's not true. I'll tell you why not, perhaps in a slide or two. So in this case, code to ISO C89 and POSIX 1003.1, which is the Unix standard. You want to compile with no warnings on all platforms. One of my current postdocs, I finally looked through, I did a build. I got him to give me all his code. I checked it out from Git and I built it. And the compilers in among a lot of chatter about unused variables and non-initialized variables had some messages he had never noticed that said, returning dangling reference from a routine. Now in C++, that means I'm giving you the stinking, rotting hulk of something that used to exist. And if the compiler can tell you that, probably it would have been a good idea to listen and fix it. So there's a lot to be said for codes that compile with no warnings, because that way you don't miss the ones you care about. Just get rid of the boring ones. It's not hard. You write equals 0. Once you've figured out that, though you know that it doesn't need to be initialized, the compiler's not as smart as you. Compilers aren't as smart as people, usually. Okay. View in 2016. Obviously true. You should use Git rather than CVS. You can use Mercurial. It's okay. I'll let you. Won't complain. I think we've basically won these battles. What we haven't done is to change graduate education to teach these things at the same time as PDEs. I'm sure you all know about hyperbolic PDEs and parabolic PDEs and all sorts of clever second-order terms that are accurate if smooth conditions, and how to handle jumps and how to do numerical diffusion. That's the sort of stuff you do learn in graduate school. You take Jim Stone's class if you haven't learned that. But you don't learn how to write big codes, and everybody these days, except a few theorists who do things on pieces of paper, and even they use Mathematica, are writing big codes. Courses are beginning to appear. For example, my APC 524 is the second largest graduate class at Princeton, but they're not part of the core curriculum. And I should correct that because, thank God, Jim Stone is teaching APC 524 this year. Thank you, Jim. So you should take courses like that. You will learn a bunch of useful stuff and a lot of very boring things, and you'll learn to work with your colleagues, which is perhaps the most important thing we teach. Last year I taught this class, a couple of years ago now. One physicist took it. There's something wrong with that. If MAE is ahead of us, if biological engineering is ahead of us, why are the physicists not realizing they have to take courses on learning the tools of the trade, like, as I say, solving differential equations? Okay, testing. Some aspects of testing are easy. When you get a problem report, you capture the bug. That's straightforward. If you want a new feature, write the test first. Some are harder. You can do continuous integration. You can do regression testing. You just have to do these things. We're using some particular technology. But some are really hard. I could have come up with an example from shock breakout or shock capture or something. How do I write a test that I correctly disentangle this collection of objects? Object, 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 object. That's a galaxy cluster from SDSS. It's not clear how you write a test that does that, because what's the correct answer? So in the case, was there a question? No. I mean, this is the equivalent of if you're writing a new, I don't know, MHD code, then you probably are testing shock tubes with parallel and perpendicular magnetic fields, where you more or less know the answer. So LSST is actually adopting an approach from HEP, from particle physics. You write a simulator, so at least you know what you've actually got. And in fact, we're even getting a particle physicist to write it, just to get extra credit. Now, of course, we're also getting the astronomers to write another version because the priorities weren't quite aligned and the goals weren't quite right, and the particle physicist thesis advisor wasn't willing to tell the particle physicist that they had to actually work with us. So you can get political problems anywhere, at any scale on these projects. I once had a friend, I think I still have a friend, who was the project scientist for a satellite called FAME and its last dying phases, who described it as a fractal disaster, which is a great phrase if you think about it. Some codes are fractal disasters. Okay, so these simulators just have to be complicated. So here's one I've missed out. Lesson 5B. This is more a software lesson than a lesson on big projects. Don't write your main program in C, or C++, or F90, or F77, or F66, or Pascal, or Modular 2, or any of the other languages that you all know and love. Lisp. Don't do it. So the lesson from 2002 was compile languages like C are the wrong tools for the job. STS used Tcl, TCL, and object-oriented C. I wrote a parser for that, and you can say things like, this is Tcl if you don't recognize Tcl. Set the min val to be some horrible piece of thing, and that's poking around down inside the C and exposing it at the Tcl level. That means you're debugging by sourcing Tcl scripts. This is really good. I think the view from 2016 has absolutely endorsed this. This is a rule that I would not even think about going into a big project any other way. Technologies change. You'd use not Tcl, you'd use Python. I don't think anybody should be writing straight C these days. You should be writing C++, even if it looks like C in many cases. You can write C++ that looks like C and use the little bits you want. I don't mean STL stuff. The compilers, if you read them, do as good a job on C++ as C. If you read the assembly, you'll discover it's 4 instructions per loop, just the way it is in C. And don't use homebrewed interfaces like my stuff written in Emacs that did the thing I showed you on the previous page. I use Swig. Now, the choice of using Swig or Boost Python or PyBind 11 or Kython or C-types or CPython is a religious matter, and I'm not going to get into religion. But I will quote Scott Myers in a very good book called Effective C++, who says, developers enjoy arguing about style issues almost as much as they enjoy arguing about which is the one true editor. And he goes on to point out that, of course, the answer is Emacs, and we don't have to worry about it. Okay. Distribute your data and your information freely. I had this conversation with various of the illustrious professors in this room just on Tuesday. The first part of it is, I wrote a mailing list manager that archived stuff on the web. It was terribly clever. It took mail, and it parsed it, and it wrote HTML. It was just great. And that solved the problem of distributed information. Make information available for collaboration as soon as possible. It's very hard to find recent data. It took years before it got into the science database. I'm not quite sure what the equivalent of this is for theorists, but I'm sure it applies. So, the view from 2016, a bit dated, isn't it? You don't have to write your own stuff that puts your mailing list out on the web. You can run Mailman or something like that. But it turns out that just because I wrote that clever code wasn't why Sloan was so successful in collaborating. It's because we built the right culture. It's possible to have all the technology in the world, and it doesn't help. People don't listen to each other. They don't communicate. They send private grumpy emails saying, Scott, I think we should do it this way. And Scott sends grumpy email back saying, you're right, let's fire Toybin. I mean, that's project management technique, but you should really do it in public. You'll enjoy saying, we should fire Toybin much more on a mailing list that goes out for whole collaboration. One thing that we didn't have in Sloan is chat. We're using Slack on this project. LSST is about to dump Hipchat, which we're using at the moment. Of course, you can waste an awful lot of time. This is the Hipcheck Tavern. This is after the Oxford meeting a couple of weeks ago. This is somebody being sarcastic about my dress code. This is what happens, what you really look like as an astronomer. You're traveling on planes. This is how you can waste a large amount of time by using tools like Slack, but they're probably a good idea anyway. You need to get the data out early. So I should have entitled this lesson, this is why I talked about this with some of you earlier, distribute the data, the code, and information freely. If you want to know where our code is, it's licensed under the GNU Public Library, LGPL actually, and that's the place you can find it. It's not a private repo, it's all out there. If you want to know stupid things that I did, you can go and run git grep on that and find the oops sort of comments. They're in there. You can go and look at the thing that says, found the bug. I'm sure that's in there. Helpful messages, remember that first line of your commit message that says why you made that change? It doesn't bother me. Everybody makes mistakes. Good people, the people at the top of the 100, not the -1, make fewer mistakes. They make the same mistake only once, you hope. When I talk to one of my postdocs and I say, "You've solved the problem, great. Is it interesting?" And they look a bit sheepish and start shuffling. And I say, "Well, don't tell me why that happened." I tend to remind them that Jim Gunn broke the secondary mirror on this Sloan project because he made a mistake. He did something dumb. He got a sign wrong in a calculation. Jim is as good as they come. He's really a very nice guy, which is a pity, but he's very smart. And he broke the mirror on a major project. You're all going to make mistakes like that. Just don't do it twice. Okay. Data distribution. That's complicated. LSST is going to do this. We're going to make alerts within 60 seconds. 55 is the official number. We say we will, and we might make 120. I don't know. You'll have immediate access to all the data if you're working in the US or in Chile, or at IN2P3 in Chance, or in the UK, including Leeds. For a while, Leeds, where my family comes from, was excluded, but I think they're in now. Or Serbia, or a whole bunch of other people. All the data will be available within a couple of years, and we're negotiating extended the access to groups around the world. Why is it so complicated? Because we're not fully funded. You get complicated things because you need money. If we had enough money to run the telescope, we wouldn't bother. We would just say, "You can have it." And this, I think I could put it in a moment. No, I'll come back to that point in a moment. This is less relevant to theorists. But at some point on the SGSS project, where we had promised to take 1 million spectra, somebody said, "Oh, we don't need to reduce the data fainter than 18.7, because that's all we need to do to get the spectra." Now, our data went down to 22.5, so it went down nearly a factor of 100 fainter than that. But it would have been easier and cheaper to only handle the data of the very bright galaxies. And most of the great science that came out of SGSS would not have happened if we had done that. And we wouldn't have found the problems in the camera. We wouldn't have found all sorts of big things. So if you don't push the limits, you're never going to know whether things are working. It's the same thing that when you find a little problem in your code and you say, "Oh, it doesn't really matter very much. You know, it's not quite conserving, I don't know, isotopic spin or something." And you say, "Well, it should be." It's worth going in and looking until you can tell me exactly why it doesn't conserve it. It doesn't conserve energy because, oh, but it's a symplectic integrator. It ought to conserve energy. It's probably a bug. And you get the same thing in data side. If you don't understand exactly what's going on, there's probably something wrong in the camera, and somebody put a Zener diode somewhere in the CDS circuits or something like that. Okay, still true in 2016. It's especially difficult because the LSST funded stream comes from MIE and MREFC. Some of you may not know what that stands for. Major item of equipment and major research equipment facilities construction. I think it really stands for mud, rebar, electronics. I can't remember what F stands for in concrete. In other words, we're building something, we're not doing science. That's a problem. If you construct a project that only builds things and doesn't do science, then you're not going to do a very good job. So in the case of LSST, we're responsible. I'm responsible, I guess. And Mario Joric, who was Scott's student. Scott's student? Yes, Scott's student. For the real-time processing, for yearly processing of all data taken, blah, 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 but nothing else. That is a problem. That's like saying, I'm going to write the world's best supernova 3D neutrino transport code, but I'm never going to compare it with the observations. I'm never actually going to run it. I'm just going to sort of run the test cases. If you're not responsible for getting the science out, then you're not going to really get to the bottom of whether your codes are any good. You're not going to find out the subtleties in there. So you really do need vertical integration between people, preferably you, doing the science, and people, preferably you or your students, who are debugging the memory managers or whatever it is. And if you don't have a significant overlap on a project between the people who really care about the grungy things at the bottom and the people who really care about the equally grungy things at the top, if you try to segment that into layers where ne'er the twain shall meet, I think you're going to have a disaster. And I could come up with examples. I think I'd better not. Okay. Catalogs, we're building lots of catalogs. So we're doing complicated things here. I'm making measurements of the shapes of galaxies, basically second moments. They're only interesting statistically. The science measuring W triple prime comes out by looking at the correlations between enormous numbers of faint galaxies. That's a very, very difficult measurement. And one of the things that's hard to do is to convey what I've done right and what I haven't done right, and how we convert that over into the project. I think that's actually something that's very obvious observationally. I mean, what exactly have I done? Do you trust me? It's also true in the case of a big code. I mean, if Jim Stone says Athena does the right thing, how do you know? I mean, you trust Jim Summer. On the other hand, he's never actually run your problem where you're trying to do a global disk model. He's only ever run a sharing box. And maybe the wave propagation works differently. And maybe you better do some testing of your own. Now, of course, if you bug him enough, he might do it for you and perhaps run a global disk model, and it's not just sharing boxes any longer. But the question of how you transfer the trust, and I really do mean trust at some level, from very technical people to very untechnical people, and I'm not going to tell you where I'm putting Jim in this list, is a real problem in astronomy. I think it's only going to get worse. Okay, so in Sloan, in LSST, we're actually letting the public get in and do their own processing. There's an example of that. How do we make that easier? So this is the equivalent of, I've taken somebody's code and I want to add some new physics. I want to add cosmic ray transport because I want to deal with that, which means I have to get the waves because they do the pitch angle scattering, all that stuff that Ellen was telling you about earlier. So, how do you make that easier? In our case, and we can think of the analogies here between the sort of things you've been talking about this fortnight, we are supporting the use of our software framework. You don't have to write your own from scratch. We're going to build on multiple operating systems, laptops through supercomputers, because people develop on laptops and they run on supercomputers. You don't want to have to run a different piece of code all the way through it. It's not trivial. There are to get things that work on small machines and on large machines. That requires you to structure things properly. Make sure that we let the public have access to the production tools we're using on supercomputers. It's not just a matter of launching one Slurm job because there are lots of sequence points. It's a more complicated data flow than running a big MHD code or something like that. I'm not saying it's an easier problem, but the problems that we're facing are different. And we're actually giving them access to a certain amount of our stuff. In other words, let the outside, the great unwashed, use our own tools, use plugin architectures. And we're planning to use something like Jupyter Hub to do that. Again, that's a technicality I think I won't go through. And what do I mean by support my toolkit? How do I say, what does it mean to support Athena? The answer is, make it good enough to make the people actually want to use it. You can put out your favorite code and nobody cares about it, they're never going to use it. Provide binary installers, perhaps less of an issue in these relatively simple non-LAD codes. We're providing things that are very, very heavily LAD because I want to version in very small scales. Operate a help desk, in other words, publish your email. And write good documentation. Ah, yes, documentation. The minimum standard for C++ documentation seems to be Doxygen, but I think it's a pretty low standard. It's easy enough to document what your functions do, but you want a lot more than that. I have not solved the problem of getting scientists to write good documentation, but I will point out this consumer for almost anything. I once came across this quotation on a mailing list. This was a few years ago. One of my favorite tech books ever. The book is like Fellini's 8.5, a self-referential and multi-readable journey through elegance and typography. I would summarize Knuth's book as being one of the worst manual books I've ever read. Incomprehensible. You have to study it in gory detail, read it 15 times because it's totally non-sequential. But if people can like the tech book, someone probably likes the stuff I write too, so I feel good about this. My current theory is to give up on scientists writing introductory and how-to documents, because people like me write how-to documents about the really clever things that only just work and are really edge-cases. They're really interesting. And did you know you could do it this way if you do it like that? But that's not what you want to know. You want to know how to get started. You want to know how to approach the structure of the code. You want to know how to make changes. So I was going to employ professional documentation people. I'm beginning to think they're going to need PhDs. I'm going to have to fluff this, blur this distinction. And though don't tell this when I'm hiring people, I'm going to look for people towards the bottom of my dynamic range of 100 for actually writing code, because they're different skills. Some people are really good at making things work, could never make new things happen. I'm hoping I can find people who are good at making things work, but could never design a new algorithm, could never be trusted to design a new class hierarchy. Okay. Documentation, we're using a Stack Overflow clone. Here's some stupid messages. This is all the way from where are we going to get our ephemerides to simultaneous RFD notes. Total grab bag. You need an editor. You can't just use something like Stack Overflow, but maybe it's the way to go. And finally, people. Science and software are not democracies. I'm not sure this country is either, but that's all right. Maybe it won't be after November. You shouldn't pretend everybody's equal. It's stupid to pretend they are. I can remember a postdoc at Fermilab. Anybody here from Fermilab? A postdoc at Fermilab on Sloan being really upset that their opinion on how to centroid a star was not given the same weight as Jim Gunn's. Now, Jim may have been wrong, but coming in, your prior is that somebody who's done this before and has got 20 years of experience probably knows more about it than a postdoc who did a thesis on something kind of irrelevant. But that doesn't mean he's right. As I say, you broke a mirror, broke the secondary mirror. So just because senior or smart people are smart and senior doesn't mean they should lay down the law. It's a difficult thing to play. But I stand by this lesson. I was right for once. The scientist dynamic range is at least as large as that of software engineers, another minus 100. I'm not going to tell you who I think makes small negative contributions to science, but they're certainly out there. You see them on AstroPH all too often. 0 is actually much commoner in science. There were several papers this week at AstroPH that I thought were a nice, clean 0 contribution to the scientific field. Budzinski's remark in this topic, which I really liked, was this paper fills a much-needed gap in the literature. Brilliance, think about it. Brilliance doesn't necessarily mean the ability to run a research group. Totally different. That's why you need people like managers. This is Fritz Zwicky, discoverer of dark matter with Walter Baade as supernova, which they explained as neutron stars before Robert Oppenheimer, who was, of course, a local boy around here. However, Jesse Greenstein, who was the boss at Caltech at the time, said, Fritz was a self-proclaimed genius, and in many ways he was one. He was not popular with the establishment, and he was often very wrong. He was an extraordinarily original thinker, but he refused to work either with modern technology or with any elaborate theoretical or measuring apparatus. So he was a problem child. Since I was nominally running things, I had my problems with him. He was a very interesting person. So Fritz was clearly an example of somebody you would not want running your research group, but you would definitely want in your department. And if you're running a big project of the sort that I've been talking about, you want people like this. Budzinski once told me he was at a meeting in Cambridge, and Fred Hoyle was there. And there was some discussion or something or other, and Fred Hoyle said, the problem with people when they get too old is they stop listening. And then Hoyle said, you know, perhaps I'm not listening as well as I used to listen either. So when I look at this picture of Fritz Zwicky, I do wonder whether my role on the LSST is to be the Fritz Zwicky of LSST. But I do not claim to be a genius. That's good. Next, avoid single points of failure. Totally obvious. If you have a single point of failure, it's going to fail. If somebody is so essential that it's proved impossible to find someone else to fill their role, you've done something wrong. You need somebody else if you've got to that point. If you've got one person, everybody gets funneled through. It's not going to work. Maybe it is, if they're good enough and you get lucky. And of course, if someone with an essential job isn't very good, then that essential component isn't going to work very well. And this is a real trap, because it's very easy on a big project to think of something easy. And you say, I don't need anybody very good to do that. You know, someone's going to do the the argument parsing, parsing all the parameter files. And then you come back a year or two later and you discover they've reinvented Fortran cards with comments in characters columns 72 through 80. They have to be in exactly the right order. The case sensitivity has to be right. And suddenly you've got a nightmare because somebody who wasn't very good got put in charge of an important thing. So putting people in the right job is the right thing to do. And it's harder than you think, especially if you're short of funding. You need to give a job to this person, to that research group. Okay. So let me update this lesson. Rather than avoiding single points of failure, hire as many people you can with the ability to be single points of failure, who could hold the crux in the project, and then manage the project to make sure that they don't. And finally, lesson 10, find some way to reward the people working on the project. We did this by saying the data is secret. We're going to hang on to it. You will get your career by, after you've spent 3 years, 5 years, whatever, making the thing happen, you will have a time that you will get to do science and nobody else will. And this doesn't work very well. One problem is this one. The promise of data in the future doesn't help a postdoc much. That's a problem in astronomy. It's less of a problem in particle physics. In particle physics, people expect to work on a project now, and that in exchange they will do science with it later, and nobody comes in later and joins it. But in astronomy they do all the time, because if you've worked on a project for many years, somebody is going to come in and make use of it. This is one of the reasons why Jim was saying, I can't just give my codes away, because if I do, somebody else will come in who has not put the work into making it happen, and they'll do something interesting with it. Now, I personally don't think that's a big issue. It's not a big issue in data because there's so much we can do. What do we do about it? My personal belief is the only way to do this is to actually integrate the instrumentation, which means the hardware and the software, into the career path. I know of one person in American astronomy who has got a job because they're good at data, a permanent job, not a soft money position. There are probably two, because I don't know any others. We have not done a good job on this. And I don't think it's changed. I wrote that 14 years ago, and in those days I knew of nobody who had built a project on the software and got a job out of it, a permanent job. Fortunately, developers are not the lonely antisocial nerds they're portrayed to be. So there's a chance that maybe we can hire programmers and they'll get us somewhere. We still have the problem of luring brilliant scientists to work on building the software. It's easy enough to get them to join the project to do the science. I'm moderately pessimistic about this. A lot of enthusiasm for OSST in the community. They're thinking about how they can help. This is wonderful, but they're not very interested in actually doing the work to build the project. So this is the negative side of my talk. I think the real problem is all about people, and I don't think the community has yet solved the problem of how to get them. How about training our successors? Let me see. This is from a thing in the EU. The EU is a thing that Britain used to be part of. The EU initial training networks. We haven't left yet. I'm not quite sure we're going to. We'll find out. So our ITNs offer early stage researchers, blah, 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 blah. What does this mean? What they did was they teach a series of summer schools. In fact, they paid for the students. They did a lot of student support of this and postdocs. So they run 2 or 3 summer schools a year. The same students and postdocs go to the same summer schools. They get to actually learn about the techniques, the instruments, the software, the statistics, and the science. They get the experts from on and off the project involved. So the one that I was first involved with was weak lensing, run by Andy Taylor from University of Edinburgh. All the lensing projects, CFHT Lens, Euclid, the European side of WFIRST, to the extent there is one, KIDS, are being run by the people who went through this training network. So it's not just a matter of teaching the students how to do weak lensing and how to worry about additive biases. It's a matter of meeting the leaders of the field, meeting the next generation leaders of the field. A workshop like this is, I think, great. You get 2 weeks, you're going to go home and never see some of these people again. You can imagine the same sort of idea where you run a sequence of workshops concentrating on different things over the course of time, where you actually get to know your peers in the theoretical computational side of things. After a couple of years, you have a knowledgeable younger generation, ready and itching to do, in my case, science with the next generation of telescopes, in your case, whatever the exciting science coming out on the computational side is. My current attempt to this is the so-called LSST Data Science Fellowship Program, and the first workshop is next week in Chicago, and that's the half talk I haven't yet written. So, finally, the emperor's new clothes. So, I've spent most of my so-called career working on processing imaging data. And one of the scary things about giving this talk is that I haven't actually done very much. When I look back at what I did, it was really pretty simple. I think about, it's just maximum likelihood estimates. I can do maximum likelihood estimates. So giving this whole talk and pontificating wildly just is an attempt to make myself feel important. So it really is the emperor's new clothes. I could pretend that I had this beautiful suit of transparent algorithms that you could have invented in the course of a couple of weeks. So I think the question comes down to, is this important? I mean, I've learned a lot along the way. That's why I'm writing another book, theoretically. You learn a lot of stuff. Is it worth learning? So when I think about that, I think it comes down to what do we actually want people to know? So which is more important? Can you do SPH in your head? You understand all about the complicated resonance structure in magnetic disks? Is that intrinsically interesting? Is that intrinsically more interesting than dreaming in CRTP, the curiously recurring template pattern, if anybody is a C++ hacker, and inventing new algorithms that enable us to do things? Which of those is actually of intrinsically higher worth? I don't know the answer. But I do know the answer. I don't think either is. I think they're both interesting questions. And this is the one you get a job to do, you get a tenured position to do. This is the one where you're going to end up working for NOAO or something like that, or down in Maryland. And which is the more valuable skill to teach our students? Most of our students are not going to end up as high-powered faculty members at the Institute for Advanced Salaries. Most of them are going to go off into business, meaning these days data mining. 10 years ago, they were going up to Wall Street, where they were doing important things to do with microsecond timing on trades to make people at Renaissance Technology rich. Now it's data mining. I would argue that you learn at least as much useful stuff learning that sort of thing as this sort of thing. You learn how to do numerical things with fuzzy problems. That's what we teach our and how to write programs. That's what we teach our students. So I would claim that the problem here is that we, as astronomers, have not really yet faced the fact that things that Newton would sort of understand, like SPH, is no more interesting than the technical side of things. And that's going to begin to become a larger and larger part of the problem. So that's all I have to say. You're going to get to your lunch early, except lunch won't be ready, so I'm going to have to take a few questions instead.